Hello and welcome to another lecture session of classical motion of a single particle. In this lecture, we simply continue our previous discussion on linear harmonic oscillator, but today we will just add a little bit more sophisticacy, and as you will see that will give us a picture which is much more closer to the reality. So, first we just have some recapitulation. We said that in a one dimension the equation of dynamics of a simple harmonic oscillator is given by this, okay, or you can write equivalently this, okay. And we say that if we know the solution of this equation, actually m r double dot is equal to f r r cap is equal to minus k r vector, this equation can also be solved easily, because since this is a central force, you can always choose a plane in which the motion is constrained. So, and you can effectively describe the resulting motion in that plane, and so you can actually always write this equation in 2D plane just like this, m x double dot is equal to minus k x and m y double dot is equal to minus k y, just right. Okay. And since they are decoupled and similar, we can simply say that if we solve one of the two, for example this one, then we can actually analogously solve the equation number 2, and we will simply write then the final equation will be. So, what will be then r? Then r will be simply x t x cap plus y t y cap. Okay. So, that is mainly the strategy, and then from that you can actually calculate r dot. Okay. So, this is the bigger picture for solving all these equations or solving the motion in classical mechanics. Now, coming back to this one. So, if you remember this equation, now the very famous solution of this equation, which you can actually find in more than one ways. So, this is given by C cos omega t minus phi. Okay. This minus is just a matter of convention, you may or may not write this minus sign, okay. And then we say simply that some vocabularies we introduced in the last lecture, and those vocabularies will be simply, okay, some people also write this as omega t minus phi 0 as well. So, we said this is called amplitude, and this is the maximum or minimum possible displacement possible. Of course, you can understand that will depend on the value of this cos of this angle, and this part that I actually did not somehow precisely say in the last lecture, that is called the phase part. Okay. Yeah. And actually, to be very honest, this is the phase part. Okay. So, the cosinus of the phase part is this part, is the oscillatory part. This is a constant, okay, and this is known as the angular frequency. So, this is sometimes slopily also used as frequency. This is time, and this is the initial phase or epoch. Okay. Sometimes in usual English accent you can also write, you can also say epoch. Okay. Yeah. Now, we also said that if we have this, then x dot will simply be equal to minus c omega sin omega t minus phi, and we have from the energy conservation we can actually write. You can also show that in various ways, but I prefer just for the first time you put the solutions directly. So, this is half m x dot square plus half k x square, and if you put them you will find this is nothing but half m omega square c square. Okay. Then we also showed that if you always whenever you have the solution by this trial method, you will also have to introduce some arbitrary constants of integration, which you can actually finally evaluate in terms of some known constants if you smartly use the initial conditions. So, we actually said that we need for 1D simple harmonic oscillation, we need two initial conditions, and they are x 0 and v 0. So, they are just the value of the displacement and the speed at t is equal to 0, or you can actually write for more than 1D, you will actually need the vectorial part, that means the x 0 vector and the v 0 vector. Okay. For 1D they are the same meaning okay, actually. Now, if we say they are the two initial conditions, then the most elegant form of the solution we showed in the last lecture, that was root x 0 square plus v 0 square by omega square cos omega t minus tan inverse or arctangent v 0 by omega x 0. Okay. I think that you can remember, and from that you can actually calculate x dot. Okay. All this thing you can do. Then we also discussed another point, that is the phase space diagram. I write this phase space diagram of a simple harmonic oscillator, and just for your information, this concept of phase space, that is actually of super importance when we will study the general dynamics, for example the nonlinear dynamics, the equilibrium, the general concept of evolution of a system, statistical mechanics, all these things. Phase space is the key factor, and we showed that phase space diagram is nothing but a plot where along the x axis you have x and along the y axis you have x dot, okay, or v, and for 1D this is quite simple. For a simple harmonic oscillator you actually have elliptic pictures. Okay. And I also somehow discussed a little bit that whenever your energy, the total energy increases, this ellipse will be bigger and bigger like this. Okay. So, for example, you go to this ellipse or this ellipse, okay, like this. But if your energy gets smaller and smaller, then you can actually have this, and whenever you have zero energy, zero total energy, then basically you see this is a very important and interesting fact for the simple harmonic oscillator. There is no negative sign in general, and that is why both the terms are positive definite. So, when this is 0, actually it is saying that when the total energy is 0, that means that both the kinetic and the potential energy vanishes at the same time, and the particle is exactly at this point. So, it does not have any displacement, it does not have any velocity. Okay. And this point we will, as we will see, when we will do in future some stability analysis while trying to do some analysis in nonlinear dynamics, we will see that this type of point is called a fixed point for the motion. Okay. Now, today's topic is such type of simple harmonic oscillation in the presence of a forcing term. So, if you remember your high school classes about differential equations, so whenever you have an equation like this, you simply said that this equation is simply, and this is a constant of course, you say that this is a second order equation, ordinary differential equation, because I have d2x dt2. So, what is this? This is nothing but d2x dt2. Okay. Then I have, if I make x to 2x, then both these terms, this term and this term, both are multiplied by 2. So, this is a linear, the second order linear ordinary differential equation, which we also say ODE. And there is another point which in general we do not mention very frequently, but here it will be of super importance, that is this part. The strategy is, you just make x, and x means the dependent variable. In this system, x is the dependent variable and t is the independent variable. Okay. So, in this system, if you make all the terms with this dependent variable and its derivatives of different orders. For example, here you just have the second order derivative, you might have also the first order derivative in case, and we will see for the case of damping actually we need such a term. Okay. So, here if you write all those terms involving x and the derivatives of x with respect to t, then if the right hand side vanishes, then we call this a homogeneous second order linear ordinary differential equation. Okay. Now, what happens if I now change a little bit this equation and I say okay, this part x double dot plus omega square x is equal to a constant. Okay. Will it simply be homogeneous equation or inhomogeneous equation? Of course, at first sight it may look that this is inhomogeneous equation because the right hand side is non-zero, but if it is simply a constant and this part of the equation is having a structure like this, where you have just a function, linear function like this in x, and all the other functions are also linear in the derivatives of x, then actually what you can do, you can simply define another variable x prime, which will be x minus k maybe, or here I have to say something a little bit more interesting. So, actually you have to make something. So, I just write this x double dot is equal to k minus omega square x, and here you simply write this as like k times 1 minus omega square by k x. Okay. And if you now simply say okay, this part I now want to take to the other side. So, I will now say okay, this x double dot okay, plus, now it will be plus omega square by k times x minus 1 times k okay, equal to 0. I will simply make this one, and or you can actually, yes, you can do this, and actually you will see that your x will be translated accordingly. So, finally, you can redefine this variable as a z variable, and according to this you will also have a z double dot with some constant over here, and finally, you will actually have a homogeneous equation in z. So, this is a pseudo homogeneous equation. Now, the very easy trick to do this type of problem is simply whenever just starting from this one, you simply do x double dot plus omega square x minus k is equal to 0, and then you simply say that okay, omega square x minus k by omega square. So, if you do now this is actually much more easier, I think, even with respect to in comparison with this part. So, if you write this and then you finally just say okay, this is my z, then z double dot and x double dot, they are the same, because you see that it is just x is shifted by a constant, and this is something which we already have used while finding. So, trick used while finding the trajectories under an inverse square law, force law, using Binet equation. Okay. Now, you see that if we do something a little bit more in this, I mean degree of modification, if I now do, now let me change the color a little bit, x double dot plus omega square x is equal to a function of t which is f. Okay. If I write this, then what happens? I can just write for my convenience, okay, just like this, where m is the mass of the variable, then it will have actually the dimension of the force. Okay. So, this is the mass of the particle, okay, or the oscillator. So, if you have this, then this is an equation where the right hand side is not a constant and it is not 0. So, this is not a homogeneous equation. So, this is inhomogeneous, or sometimes we also say non-homogeneous, and actually the non-homogeneous vocabulary you will see often, non-homogeneous second order linear ODE. Okay. So, you see that here I have a function of t and I have to now find x, so that this equation is satisfied. Now, you can actually by trial and error you can somehow find a solution which exactly solve this, let us say by chance, by luck. Okay. Now, will that be the total solution? There we have to make a little bit caution. Let us say I have an equation which is non-homogeneous linear second order ODE. Okay. Then if I have x 0 to be its solution when this equation is homogeneous, that means x 0 is such that x 0 double dot plus omega square x 0 is equal to 0. And we have our x 1 solution. So, both of them are actually variables, they are not numbers or values, they are variables. So, x 1 is the solution for the whole part. So, then we can write x 1 double dot plus omega square x 1 is equal to f t over m. Okay. Now, if you add the two, you will actually have adding, you will have x 1 plus x 2 whole double dot plus omega square x 1 plus, I am sorry, this is x 1 plus x 0 whole double dot plus omega square times x 1 plus x 0 is equal to f t by m. So, you see that if although x 1 was just found as a particular solution for this form, but since x 0 is the solution for the homogeneous part, even if you add this to this part, it is always giving you the correct solution of the whole equation, and that is why the whole solution will be x 1 plus x 0, and this x 0 which is the solution of the homogeneous part, okay, is called a complementary function. Sometimes we say CF, and x 1 which is a solution which is very much specific to this form, then this is known as a particular integral which is p dot I. When you add them both, okay, then only you have the total solution, and whenever in an equation you want to find the proper solutions and you using the initial conditions, you have to remember that first of all you have to obtain the total solution and not just the and not that you just obtain the particular solution and the particular integral and then you immediately use the initial condition. You have to also obtain the complementary function, then you have to write the sum of the two as the total solution, then only your initial conditions should be applied to those solutions. Okay. Now, how to solve? We understand everything. Now, for this system, how to solve? Okay. For that, what we will do, so I just write this x double dot plus omega square x is equal to f d by m. So, in general, if the question is how to solve such equation, of course, we know the complementary function will simply be the solution of a simple harmonic oscillator, that we all know, but what will be the solution or the particular integral for this equation? The answer is we do not know. We have to know the proper form of capital F of t, and in most of the cases a very interesting situation arises when we assume that the forcing term, that F. Okay. So, this is a forcing term which is somehow giving the energy inside the system continuously. So, if this F is also a periodic function, okay, then we actually can have some very interesting phenomena which we can relate to our everyday life. For example, if you go to a park and there is a swing, okay, and you are sitting and some of your friends, they are just periodically pushing you, okay, then what happens? So, this is actually an oscillation under a periodic forcing. On the other hand, if you are somehow hammering periodically a tuning fork, okay, and then it is also oscillates under a periodic forcing. Okay. Such things are always there. Whenever I mean, you have also learned about the famous example that whenever group of military people, they are doing parade over a bridge, okay, then also there is a possibility of forced harmonic oscillator. Okay. Now, just to tell you from very well known interesting examples, we often write f cos gamma t plus beta by m as the form of the forcing. So, the forcing is periodic and gamma is the frequency or the angular frequency of the forcing, okay. And that actually the external agent knows. This is not something intrinsic of the system, and beta is the initial phase of the forcing, initial phase of the forcing. Okay. So, if you now just write this and you say that then I have to find a particular integral of this equation. Then what to do? Okay. Then of course, there is a small challenge. Okay. So, then I have to actually come out with a trial solution. Let me search for a trial solution where x t will be given by b cos gamma t plus beta. You see, that is very interesting that I am taking a trial solution in which the displacement and the forcing term has the same phase term. Okay. This cos term, cos gamma t plus beta, okay, and this thing they are identical. Okay. That is also coming from some experience where we have seen that finally a system which is forced and oscillating, finally it settles down to exactly at the same oscillatory motion as that of the hammer or the periodic force. Okay. And if we do that, you just can then write what will be x, sorry, what will be x double dot. So, I have to just calculate x dot. From that, x dot will be gamma b minus sin gamma t plus beta, and x double dot will be gamma square b cos gamma t plus beta. If I now put this thing and this thing here in this equation, then what we will get? We will simply get gamma square b cos gamma t plus beta plus I mean there should be a minus sign actually here, sorry, there should be a minus sign because there is a minus sign and ddt of sine is plus cos, yeah. So, minus plus omega square x is b cos gamma t plus beta, and on the other hand you have f by m cos gamma t plus beta. You just assume that cos gamma t plus beta never vanishes, and that is why you will have a form which is superb. It is simply b is equal to f by m omega square minus gamma square. Whenever you have this, then you know x t is equal to f by m omega square minus gamma square cos gamma t plus beta. And here you in general stop and you say that okay, I am done with the solution, and that is where you commit a mistake. What is the total solution? Well, I should not forget there is the solution from the homogeneous part or the complementary function, which is given by, let us say, some I do not know, like some c cos or c, I mean here I just write it e cos some omega t plus alpha, I can just call this one without any problem, plus f by m omega square minus gamma square cos gamma t plus beta. Okay. Now, you see this omega, which is the frequency of the oscillator without any force, is known as the natural frequency of the oscillator, natural frequency. Now, everything is very good, only problem is caused when omega is equal to gamma. This is superb as equation if omega is not equal to gamma. For omega is equal to gamma, you will see that the second term on the right hand side is actually blowing up, but you know that this term will not blow up and this term will also not blow up. Okay. So, because I mean otherwise there is a problem, and also if you just go to the original equation, if your x, now you can actually think in the other way around, that let us say one part of x is blowing up. So, x is actually blowing up, just you assume, then this part is blowing up, this part is also blowing up because x is there as well, but this part you are giving a force. So, which cannot blow up because you are controlling that and you know what you are giving. Okay. So, something blowing up, something infinity will be equal to finite. So, what is the conclusion of that? That is, this solution is only a good solution when omega, the natural frequency, is not equal to the force frequency, okay, the periodic force frequency. If they are equal, then we have to think for another type of solution, and what is that? That we will see in the next lecture. Okay. Thank you.